All right, so the last video was called a deeper dive into quadratics. And it's basically a prerequisite for what we're going to be talking about today. So if you haven't seen a deeper dive into quadratics, I strongly encourage you to go there right now versus this video, which is same topic, just not going to explain rates of change as completely perhaps as in that other video. But talking about the same concepts repetitively, I think is extremely useful. I think it's almost something you just have to hear on a regular basis are the concepts underlying the techniques and procedures that we're going to be looking at today. All right, so enough said on that. So this video is going to be 5 quadratics. The first one I'll go through very slowly. The next 4 more quickly. And we'll look at the interplay of the rates of each term and how we can use that for some quick information. 2 or 3 of those quadratics, user-friendly numbers, I'm hoping that we can answer. Sketching it, the roots, domain and range, 30 seconds or less, okay, on 2 of those when we get there. We'll build up to it, take our time, no rush. In the previous video, we looked at a 2x2 square or 3x3 and how the areas were changing using some table values, small change in x, 2.001 compared to 2 as an input. And we saw some interesting patterns that the change was twice the x value. In other words, if I layer change from a 2x2 and I keep layering change, and I keep layering change, eventually I get a bigger square. And that net change in area is something you'll study how to find in calculus. We're talking about rates right now, trying to understand rates. And we also did one at 0 and found that at 0, the rate of change in the ax squared plus bx plus c model, that bx plus c was the tangent to the y-intercept. So we're towards the end of the semester. We've been putting quadratics in graphing form a certain way for 3 months now. And I'm going to show you another way to do it. And I did in that deeper dive into quadratics. But let's start with the basics. Let's generalize now that we're towards the end of the semester. Ax squared, that first term, if a is positive, cup shape up. If a is negative, cup shape down. Throwing the next term in. Let's add a bx term. If a is positive, cup shape up, and if b is positive, you're on the increasing side. And of course, that means 0C is not AOC. See earlier in the news, but 0C is the rate of change at that location. Minus ax squared plus bx, cup shape down because it's negative. We got a negative a term. And I probably should put a negative a term, a positive a term. Probably should have done that. All right, so we're on the upside. You always follow, your finger always follows from left to right when we read graphs. It's kind of how your eyes follow reading on a page, left to right. So that's how we read graphs. Pick up my marker cap. Okay, and so it gives me some quick information. Now, what happens if A is positive? A is positive, cup shape up, but B is negative, then I'm on the downside of that curve. And if A is negative, cup shape down. And if B is positive, I'm on the upside. We zoom in. We can see that slope, B, right there, positive B. And generalizing some more, if x squared changes variably 2 times the x value, and I multiply that by a, then I'm going up. This is a scalar. I end up having a formula for the rate of change of a quadratic, 2ax, which means that at x is 2, I am going up at 2 times 2, 4 to 1. If x is 3, 2 times 3, 6 to 1. if x is 4, 8 to 1, so on and so forth. Boom, acceleration. Right? So, and that's also true here at 5, negative 5, minus 10 to 1. At negative 4, minus 8 to 1. That's actually a bigger number than that. This number went up by 2. Add 2 to negative 10. Yeah. All right, so how can that help us graph from a different perspective? Well, in that previous video, we talked about q of x giving us an input and an output. Q prime of x is telling us how things are changing at that x value. And 2ax simply means if I double that number and put an x after it, I'm telling you how that's changing. It's twice as fast as x squared. And this is constant change. We've talked about how to spell constant. K-O-N-S-T-A-N-T. My grandson says I'm supposed to use a C. I tell him he doesn't know what he's talking about. All right, so this is constant change. I don't care if you change by 0.001, then you're going up 12 times that change. I don't care if you're going up, changing by 100 units, then you're going up 1,200. Yeah, that's how you're changing at that instant. 1,200 divided by 100, still 12 to 1. I almost misspoke there. So this is called the derivative. And when I set it to 0, I'm going to have a flat moment on a curve. Because minus 3 times 4 is minus 12. The quadratic is pulling down at 12 to 1. Linear terms going up at 12 to 1. Got a flat moment. And if I put 0 in, I get 12. Oh, what a coincidence that at 0, when x is 0, I'm at negative 5. And I'm going up at 12 to 1. It's interesting. I find that very interesting. Yeah. And how far is it from 0 to negative 3? 3 jumps. 3 jumps of 4. 3 jumps of 4. Yeah. Oh, 3 jumps from 0 to, oh yeah. Interesting. So what are the roots? Well, I got to find out where I am at negative 3. I need that value. I need that k value because there's a nice little formula for the roots, which means I already have this one. I already have that plus minus square root. I know what a is. It's given. It's a 2. All I have to do is figure out where 0 is. That's negative 5. So 0 is up here somewhere. 0 is up here somewhere. And I want that x value. And I want this x. I want this one and this one because we know the fundamental theorem of algebra says there's 2 answers to this equation. They might be real, they might be imaginary, or they might be what we call a double root, but that's another matter. So how do I find k quickly? Well, we drop it in. Negative 3 times 12 is negative 36. We've looked at the shortcut. Minus 18, minus 5, negative 23. We've been doing those lesson sets now, 30 or 40 of them, for God's sakes. We do that in every lesson set. And so how do you get from negative 23 to 0, to height of 0? This is y equals 0 up here, which is higher than minus 5. That's y equals minus 5 right there. 0 is more. Well, I'm measuring from negative 3. I'm looking to the right, which is what the plus sign means. I'm looking to the left, which is what the minus sign means. And I have to go up 23, which is the opposite of k. Up 23. There's my roots. Domain. Well, easier to see domain if we put this in graphing form. So I've got minus, where am I? Minus, a term. So q of x, q prime of x, is 2x plus 3 squared minus 23. Took me a moment. All right, so what number can I add 3 to on the number line? I find a number on a number line. Can I look 3 units to the right? Yeah, I think so. Can I square every number? Is there a number I can't square? Can't think of one. Is there a number I can't multiply times 2? Can't think of one. Can I take 23 away from every number? Is there a number I can't take 23 away from? Not on the Rene Descartes coordinate system. Good for you, Rene. Rene Descartes. So the domain we'll say is X values, and they're all reals. Any real. You can use anything you want. But I got news for you. Your Y values never going to get lower than -23. That's a minimum. So my Y values are greater than or equal to -23. Right, and we're going to try to do that with the next problem. And the one after that, we'll try to come in under 30 seconds. And then after that, we got some that aren't so friendly. So we got three more that are friendly. Friendly, I don't need a calculator. I don't have to work with fractions. Okay, we'll do a few of those just to get the skill level up a little bit. And then we'll do one that, more of a typical quadratic formula type problem. But we'll still come at it from this perspective, just to see that things are the same. All right, so what do I have? Cup shape up. What side is my y-intercept on? The downside. And I'm at -5 again. So 0 gets me -5, and I'm going down at 12 to 1. That means this is a positive x. Let's use the derivative. Since you're going to be studying rates of change of all the functions, it's such a short period of time if you keep going up the ladder. 2 years to you seems like an awful long time to me. To me, it seems like a snap of the fingers. So very soon, a lot of changes coming your way. You're going to have to conceptualize the mathematics in 2 years. Got to start thinking deeply. Take a little practice, ease your way into it. Might be helpful. All right, so again, minus b over 2a, right? But we're not doing it that way now. We're going to do it from the perspective of 6x minus 12. So I now know that's 2. Okay, 6x minus 12. Okay, so that's a 2. And if I put a 0 in, oh yeah, we're going down at 12 to 1. Yeah, if I put a 0 in, oh, here, sorry. This is the rate function. This is all about rates. Yeah, the interacting variable rate with the constant rate. And so now if you put 2 in, you got -24 cut in half is -12, -5 is -17, which means you got your roots. Sorry, x equals 2 plus or minus the square root. -17 becomes +17 divided by 3. We got our domain, reals. That doesn't change with the quadratic. And what's the range? The range is greater than or equal to -17. I think we're done. Now, of course, if I wanted to go backwards to find out this, well, that's another skill on the test. Let's do it one time. Let's do x minus 2 equals plus minus the square root of 17 over 3. Let's square both sides. Let's go to x squared minus 4x plus 4 equals what's inside, 17 over 3. Sorry, I butchered that a little bit. And you can still see it. Well, let's multiply by 3. You get 3x squared minus 12x plus 12 equals 17. Take 17 away. I may have run out of space, and you can see we're right back to what we started from. Yeah. And of course, completing the square brings us back down to this. Trying to tie a little bow around some of the things we've been working on. All right, so now, your turn. Let's see if you can pause the video and see if you can answer sketch, roots, domain, and range. 30 seconds. Okay? I'm just going to keep going, but you pause the video and have a little go at it. Now, I'm going to take a little more than 30 because I'm still going to write some things down that I wouldn't write down. And maybe I'll do that on the last one, things I wouldn't write down. But right now, I'm seeing this. I'm seeing this. I'm setting it there. I'm seeing that. I'm seeing, mine's +5, excuse me. I'm seeing 0 gets me 7. I'm seeing 5 goes here, so that's 157. So I'm seeing 57 here. So therefore, I'm seeing 5 for my roots. I'm seeing 5 plus or minus the square root of minus 57 divided by minus 2, right? And I probably would not have put the minuses in there, but here's 0 down here. So we know we have real roots, and the minus corroborates that. I know that a main is real, so that nothing's changed there. And the range is y values less than or equal to 57. Okay, and I'm talking to you. I'm not really putting much intellectual activity into that. It's pretty old hat for me because I've done so many. So what's the secret to getting skillful? Practice. Let's go for it again. Pause the video. See what you get. Did I do a negative, negative? Well, let's make this one positive this time. Since the last one was cup shape down, let's reverse it. Let's go cup shape up. You pause the video, you have a go. This time I'm not going to say anything, just going to do it, and just for fun. Yeah, I think that's it. Now I'll go check and see if I made a careless error. I hope I didn't, because that means I got to erase everything and do the video again. I don't feel like it. Where's my coffee? That would help, just in case I have to, have a moment here where I go, oops, got to work hard again. All right, so don't have any coffee with me. Anyway, so minus b, 18 divided by 2a, 6. Okay, so that corroborates that. So does what I did in my head was 6x minus 18. I did it that way this time just to get that 3, which means you could have just written this immediately. It's saved a little work, little thinking, just get the root going. And then if you drop a 3 in, I get minus 54. Cut in half is minus 27. Minus 27 plus 7. I'm feeling pretty good so far. That's minus 20. But in the roots, minus 20, I got to go up to get to 0. Right? To get to 0, I got to go up 20. Right? So that kind of highlights inverse operations. And if I got multiplication, again, we'll put it in graphing form here. We got 3, we got x minus 3. Sorry for the duplication, but that's what we got. That's in graphing form. So I hope you can see all of the steps for solving, all the inverse steps to isolate x. Add 20, divide by 3, measure from negative 3, which means you get a positive 3. Kind of explains everything. So there's a ton of quadratics that you can do this way that cuts down on time and effort. If you put the effort in, it becomes an effortless pop. If you practice with effort over time each day, should become effortless. All right, now we're going to do one that's more aligned with the quadratic formula. I'm not saying which is quicker or which is easier in this instance. I'm still not sure. Let's have a go and find out. And then at the end, I want to talk about rates of change for other functions, just to give you a little sense of where you're headed in life, what you're going to be studying. All right, so let's go this route. Let's not hurry this one. Let's look at the derivative being 4x minus 3. So therefore, when does that equal 0? When x equals 3/4. So over here, we can start our roots. We're measuring from 3/4 plus minus the square root, and we already have a. A is 2. So the only thing we're missing here is the k value, hk. It's fraction. We don't like fractions, but we can deal with them. Minus 3 times 3/4 is minus 9/4. If I cut that in half, it becomes minus 9/8. And if I add 7, 7 is 56/8. And if I put those together, I get positive 47/8. Okay? Which means over here, I want minus 47/8. And when I divide by 2, that division gets factored in. I've got that. And now, if I change that, I've got imaginary. So there's my roots. All right. What's the domain? So 47/8 was, I lost track here. So h is 3/4. I have imaginary roots and I've got a cup shape up. So therefore this has to be 47/8 is this number. Okay, and zero's down here, so that's why I've got imaginary roots. Now let's do the quadratic formula, see if we can get back to that. And if not, I gotta go make a cup of coffee, cry into the coffee cup, and because I don't want to do this again. So minus b, the quadratic formula, finding the roots, plus or minus the square root of b squared, minus 4 times a, 2, times c, 7, all over 2a, 4. All right, 3/4 corroborates that. 8, 7, 9 minus 56 is minus 47. Okay. 4 is outside, so therefore I could put that 4 there. And now, if I want to move that inside, I've got the square root of 16, and that's imaginary. Okay, so it corroborates it. I probably would go quadratic formula here. I'd probably do very quickly the discriminant b squared minus 4ac, do that first, and then put in the other numbers as a little shortcut. But it's the same. All right, so the domain again, all reals in the range greater than square root of 47/8. That's 47/8, excuse me. 47/8. So y value is greater than or equal to 47/8. All right, so it does get awkward when you start getting non-user friendly numbers, but we're talking concept here. Talking concept. Slope on the decreasing side going down at 3 to 1 when x is 0, and seeing why those work and starting to think about them now, so that when you get to that higher level, the work you do and the symbolic language you use to prove that these things are true, you've got a much better chance of knowing what you're doing, knowing what you're after, putting your eye on the prize. And you got to have a foundation on what these graphs look like, what the sine function looks like. Let's look at one period of the sine function, which I think is becoming familiar to you, at least part of the class, right? That familiarity. We're practicing the sine of 2 pi over 3, which is root 3 over 2. We're hoping that you know that that's about 0.87, all these things talking about repetitively. What you might not know is, at this instant, you're going down at a 1-to-2 ratio. At this instant, right there, the sine of pi. I'm at 0, 1. I'm also going down at -1. At 3 pi over 2, the sine of 3 pi over 2. We're going to learn how to do that in the next 2-3 weeks. It's not hard. Some of you have already got it with just 2 minutes a day for 3 days in a row. All right, so that is -1. But the slope at that instant is 0. Wow. Can't imagine what the cosine of 3 pi over 2 is. Can't imagine what the cosine of pi is. Just don't know where to look for that number. Yeah. And the ln function. Wow, the ln function. Interesting numerics about the ln function. I hope you can see that, because I can't see the screen at all. Yeah, so here's the ln function. We got some numbers we're familiar with now. The ln of 3, 1.1. Yeah, of course, I'm not sure you knew that at that instant, when x equals 3, the slope of the line is actually going up at 1/3. At 2, I'm actually going up at a 1-to-2 ratio. At 1, I'm actually going up at 1-to-1. And at 1/2, I know my location is -0.7. That's that altitude, because I know the x-axis, right, intersects the ln curve at 1, 0. Yep, and when x is 1/2, boy, the slope there is 2 when x is 1/2. And 1/3 when x is 1/3, I'm going up at 3-to-1. That kind of looks like the ln shape. Yeah. Well, Very short time, you're going to be studying why that works. So it's very helpful if you actually know what the LN curve looks like, because if you don't, it's pretty hard to talk about how it's changing. So the things you're studying now, yes, they are foundational and they will support future study, because going at a certain rate, you step off a ladder, you're on the first rung, you hit the ground at a certain rate. Very different if you step off the ladder when you're painting the house and you're up kind of high on the ladder and you step off. You get a little different rate at which you hit the ground. And I think it's probably important when you're working with physics to know the rates at which things are changing. That's where you're headed. All right, so much for that. And now that'll be hopefully something we work on for at least 2 or 3 more weeks before the last set of tests. All righty. Have a good day, everybody.